Alright guys, let's bring this home. Bearings, part 3 out of 3, real life example. We got a real life example question here that has to do with a ship traveling. We need to make sure that we draw a true representation diagram of this information provided here in order to answer the questions here. Whatever the question is asking for will not necessarily dictate how your diagram is drawn, but it will need to be there are certain features that need to be highlighted from your diagram. It needs to stand out, it needs to be obvious, and sometimes finding the link between the two isn't all that obvious. You will be using some form of trigonometry. There needs to be some form of trigonometry within the question, and if there isn't, it's actually going to be quite tricky or difficult to be able to answer this question. So for now, let's have a look at this question. A ship travels due south for 5 kilometers. A ship travels due south for 5 kilometers. Then on a true bearing of 120 degrees, should say travels for another 11 kilometers. Now, the obvious question or the easiest question would be, how many kilometers did the ship travel? And you would say, oh, that's simple. That's like 16 kilometers. Just add 5 and 11. But you guys are in year 10 general maths. It's not going to be that simple. The first question is going to be asked for how far east, so to the right, how far east the ship is from its starting point, correct 2 decimal places, and how far south the ship is from its starting point. Alright, so we're looking for how far away this way, how far away this way, east and south. Now, let's draw this diagram. It's not going to be accurate as long as the information portrayed on there is correct, and that's all that matters. A ship travels due south for 5 kilometers. Okay, so we're going to have a starting point, which is here. This is where the ship started, and it's going to go south, which is down. Let's assume that that's a straight line, and this right here is 5 kilometers. Okay, so the ship goes from there to there, travels 5 kilometers, straight line down, chug chug, woot woot, let's do this. Then on a true bearing of 120 degrees. All right, let's dissect this. True bearing of 120 degrees. And it's a true bearing not necessarily from where it started, but where it is now. So you can picture this as almost like the new origin. Oh, so if this is our new origin in a different color, I'm gonna put these 4 compass directions of north, south, east, west, and using that as our origin, we're going to go on a true bearing of 120 degrees. So true bearing 120 degrees, starting from here, we'll keep going. We'll keep going. I'm going to get a different color for this one. It will go, and that's at 90 plus an additional 30. So just as a different color, 120 degrees is equal to 90 degrees plus 30 degrees. And I've specifically written this down. It seems kind of obvious, but there is a reason why we'll need to write this down. So here's our true bearing of 120 degrees that has been created from this new spot here after 5 kilometers. So the line will be here, like that. And how long this line is 11 kilometers. So this will keep going over here, and that is 11 kilometers. Now, a lot of people, when they first attempt this type of example, most likely will get a different solution or a different diagram, and then therefore a different solution to the one that I have here, or any type of question similar to this, because this is what gets them then on a true bearing. And here, this word here, then on a true bearing. Then on a true bearing. So it went 5 kilometers, then on a true bearing from that spot, from this new hypothetical origin, a true bearing 120 degrees, which is here, and then 11 kilometers after that. Okay, so we've got our diagram. So our ship has started here, it's ended here. And now what we need to figure out is how far east the ship has gone from its starting point, correct to decimal places. So we're looking for this starting point. How far along has this ship gone from here to this direction here? And if we keep going and going and going, what I might do, let's see if I can move this over there. Oh, look at that. That's this Photoshop full of wind. We're gonna see how far laser select. Oh, I knew this was gonna be too good to be true. I'm just gonna pause so I can fix this. Okay, so I think I fixed it. Yes, yippee. Okay, so how far along east has it gone until it matches up with its endpoint? Let's just assume it ends there. Okay, so the endpoint here. So we're getting this distance from here to here, and that's going to be for A. And then B is how far south the ship has gone from its starting point. So for B, we are looking for this point here all the way down until it gets to its endpoint here. So we're looking for that length. All right, the very first thing I'm going to do is, it's not obvious to do, but I am actually going to draw a right angled triangle. Oops, a right angled triangle that goes from here to here. There's a 90 degree here, and here we have a right angled triangle. Now it's not obvious to do this, okay? This will help us out for both of the questions. And the second thing I'm going to put in, is, remember this fact here where I said that this 120 degrees is a 90 plus a 30? Well, there's a 90, meaning that angle in here has to be 30 degrees. Alright, there's a 30 degrees. Hold on a second. We have a degree, we have a side length. This is where that trigonometry comes from. Could be sine, cos, or tan, we don't know yet. We'll look into that later. But for now, this triangle will help us out with at least question A. How far east has the ship gone from its starting point? Well, we know that from here to here is the length we're looking for. Isn't that length exactly the same from here to here, which is part of this hypothetical 90 degree right angle triangle? Why don't we redraw this triangle like so and kind of fill in the blanks? We have a 30 degrees, we have 11 kilometers. Now let's label this. What we're looking for is this length here, which is this length that I copied here, which is this length that it came from, which is our x kilometers. And what we do know is that we have been given the hypotenuse side, which is h, and we're given the adjacent side in relation to the angle that has been given, RA. So let's write our trigonometric identities. SOHCAHTOA. Which one uses A and H? Well, that has to be the cos, and cos is equal to A over H. So let's write this angle, trigonometric identity with the angle down. The cos of 30 degrees is equal to our adjacent, which is x, which is what we don't know, over the hypotenuse, which is 11. Alright, and this is where our trigonometry is going to help us answer the first question. Whenever there is a number on the bottom that has been given, and what we're looking for, our unknown, is on the top, you just get the bottom number and you multiply it with the trigonometric identity. So in this case, 11 times cos 30 degrees is going to give us our x. So in this case, x is equal to, grab my calculator out, 11 times cos 30 degrees. Now, if you get this answer that looks like this, make sure that you press the SD button. So from standard to decimal format, and standard just means it wants it in a fraction form. You get these little square root popping up. You don't want to look at that. You want to get this. So in this case, 2 decimal places, 9.53. So x is equal to 9.53 kilometers. So all this is saying is, after this ship has traveled from there to there to there, how far away east it is from the starting point is 9.53 kilometers. Okay, so therefore the ship is 9.53 kilometers east from its starting point. From its starting point. Cool. This is where trigonometry has actually helped us. We've got a really simple set of 3 information: south, 5 kilometers, bearing, and another 11 kilometers, 4 sets of information. And just using trigonometry, we found how far east it is. Now let's find how far south it is. Because the next question is asked for, find how far south the ship has gone from the starting point. So we know that there's automatically going to be a 5 kilometers. That's how much it's traveled south to begin with. But what we're really interested is this point, which is here, which happens to be the same length here, which is also from our diagram, but it's just looking for something a little bit different. So again, I'm going to draw this diagram out. And again, I'm going to fill out the information that I do know. We've got 11 kilometers. There's our 90 degrees. There's our 30 degrees, which is in here. But the side that we're interested on isn't necessarily the adjacent this time. It's actually the opposite, which is this side here. So we've got our hypotenuse, again, opposite the 90 degree. And we've got our O, which is opposite the angle of interest, or angle that has been provided. The trigonometric identity that uses O and H is sine, and sine is equal to O over H. Or in other words, sine of the angle, which is 30 degrees, is equal to O, which is X, over H, which is 11. So this time to find the other side looks very familiar to this identity here. The only thing that's different, instead of using cos, we're going to use sine, because we're trying to find the other side. And so in this case, 11 times sine of 30 degrees is going to be equal to our x. So our x in this case is 11 times sine of 30 degrees. And again, press the SD button, 5.5. So X in this case is equal to 5.5 kilometers. However, just be careful. We have found what this length is from here to here, which is good. That's not enough information. We also have to consider the additional 5 kilometers that it's traveled south to begin with. So therefore, the ship is, and 5.5 plus 5 is 10.5. So the ship is 10.5 kilometers south. It was east and south from its starting point. Alrighty. And that is how you answer a real life context question using true bearings for the information that has been given with help of the trigonometric function identity sine, cos, and tan. A lot to take in. Remember, we are up to lesson 4, lesson 5. This lesson 4 of bearings is the trickiest topic in all of general maths, in my honest opinion. Okay, and the reason why is because we have to dissect a question here and make a diagram from it. The diagram is hard to get from one thing to the other, is the trickiest part, especially if you're a visual learner. If something has been visually given to you, cool, we can try to answer it. If you have to make the visual, different story, because there's so much room for error when it comes to interpreting some of the fine key languages within the question. Okay, this is a tricky topic. So if a lot of this has kind of gone over your head, as long as you can at the end of this bearings topic be able to try to somehow, some way apply a trigonometric function to a bearings question, regardless of whether it's wrong or right, then you're doing most of that work there. Okay, and the practice just comes from fine-tuning the diagram that you draw. Hey, if you get the diagram right and you get the trigonometric identity right, booyah, you're doing it correctly. Okay, so don't beat yourself up if this is too much of a tricky topic. For others, you probably think, hey, this is actually quite simple. We just kind of have to put everything into place and then use our calculator to solve it. Rely on the solutions that have been provided. Okay, I know it seems counterintuitive to just look at a solution before you even attempt a question, but it's somewhat good to see what the end result should be. So you have your solution, your end goal, and you'll be like, okay, how do we get to that end goal? And if you've done the question and you've got your end goal and it's incorrect to the answer, then you can say, what have I done wrong? So use your answers to help you. Don't use it just to cheat, to say, yep, I've done the work. The answers are there purely to give you a solution. All right, nearly 20 minutes. That is me done. Part 3 of 3 of bearings. I'll see you in the next video, which will be our last video for this topic of trigonometry, trigonometry in 3D. For now, your log sheet requires you to do the question 1 to 4 for foundation, 2 to 6 for standard, or 2, 4, 6, 8, 10 for advanced. If you feel not that confident with this topic, probably stick to the foundation type of questions. But if you understood what I was talking about, try standard. Okay, and if you're confident, go for advanced. Page 287, guys, exercise 4D. I'll see you guys in the next video.